Hi guys. Um, in today's meeting, we will again use the scikit-learn library. It's a Python-based library for machine learning and related subjects. The idea today is to show the vectorizer functions of scikit-learn and take a look at the generated inverted indexes, so we can see, like, depending on the metric that we want to use, the most frequent terms, or the most frequent terms depending on a specific metric. Let me share my screen now. All right, so you guys should be able to see my screen now. I have a notebook already prepared for this presentation that I'm about to give today. I will make it available along with the data that it uses. This notebook is actually based on my thesis work. So the data that we are using is a sample from Stack Overflow. I can show you quickly the format for the file that we are about to use. It's a CSV file, so so the first line would be the header. So it pretty much comes with the labels for the data entries. So let me show the first line here. Yeah, take a look. There's a couple of things that were pretty much collected from a dump that Stack Overflow publishes from time to time, and the most significant things that we will use is the post body and the post title, which is this. Here's the body, and where's the title? Here's the title. So you can just extract exactly the column that you want from a CSV-like file. The last 20 columns are answers that are given to a specific question. So each row actually is a question from Stack Overflow, and these 20 last columns are answers that were given to these specific questions. This is a data aggregation that was done to actually come up with this format. The data originally was not in this format. Originally, Stack Overflow doesn't actually differentiate between a question and an answer, so they just consider everything as posts, and depending on the flag, that's how you differentiate that. So to our case, it would just be easier to have a data like that, like in this format that you are seeing. Let me. This is a notebook that I'll make it available after we finish the presentation. This notebook uses a kind of library that I'm writing, which is just not really a library. It's just a collection of functions that I use. So to not make the code too large, I keep putting my functions into this file, and I just call the function from there, so it makes the notebook appearance more clean, and I prefer to do that way. So in this case, I'm just using actually two functions from this library here. The first one, it gets the contents from what I call knowledge bases, which is just actually a text file, which for each row in this file, I'm going to show actually an example of that one also. For each, like in the case of the knowledge base, we have a couple like 6 knowledge bases, I believe. So I can show like the first 2 lines, 3 lines, so to give a more easy understanding. Let's take knowledge base Android, for instance. So here actually is a bit hard to get. But let me just show the first line then, because depending on the article that you are seeing, this whole thing here is a line. So this line represents an article or an entry on this knowledge base. So I have an Android knowledge base, which is a text file, and for each line I have an entry. So that's how this file is, let's say, formatted. I also built these knowledge bases from different sources. So like for in this case, for Android, I actually got the Android documentation. I downloaded it and I processed it in order to come up with a more because like Android uses an HTML kind of documentation format. So I just formatted it to make it more feasible to my case here.
Did you scrape data from their HTML site?
What?
Did you scrape some data from their website? I mean, how did you got this data from their?
Oh, in this case, I got it from Android, the IDE. How's it called? Android Studio, right? I think it's Android Studio.
Yeah, Android Studio.
Right. Yeah. So I got Android Studio has the option to download the SDKs, and also there's an option in this downloader also to get the documentation. So I just use that. But then that comes in HTML format. That's the same format that you can consult online. Right. If you go to the API documentation website for Android, you're gonna have the same kind of content. I didn't use any, in this case, I didn't use any web scraper or something like that. I could have done that also. That way also.
Yeah, that's what I was asking. If you got this data from online website, then you would have used some scraper.
Yeah, right. I prefer not to, because there's a lot of people which actually complains about using web scrapers because it's kind of an overload on web servers, and there's a lot of requests that you generate on a short amount of time. So they don't see that as a good thing. So I prefer trying not to. This way is also, at least to me, it's an easier way. I just get everything, and then I just have to process the data. Sometimes it can be challenging, the process, even if you have the data, on your disk, but it can be still a little bit challenging. I use a combination of regular expressions and beautiful SOAP parser to try to filter everything and get in a more in a better format. In another time, I can also show how, more detailedly how did I do that. So here just really to give an idea of how this data looks like. That's the goal, at least right now. So as I was saying, the first function here, it just takes the knowledge bases, and then in my case I have knowledge bases plural. So I get these different sources. I get everything in a single thing, because for my processing I don't need to actually differentiate between these, other than knowing what I call tag. So the knowledge base that comes from the Android, the entries that come from Android knowledge base, I just have to know where it came from. That's it. What I call tag. So the tag for these entries will be Android. Then let's say JavaScript. I just will like same thing. I will put a tag JavaScript for every entry from the knowledge base for JavaScript specific things. Yeah. So that's it. That's the only thing that I need to know that differentiates between one knowledge base and the other one. So this is represented in this second variable here, which is called kx tag.
Okay.
And the first one is just the raw text from the knowledge bases. So each row is an entry. And then the second line, it's a little bit more elaborate, but it does something also similar. It reads a lot of things from one single file. So that file that I showed, the first one, the 5K something, this file, the CSV file, is the origin of this whole thing here, this whole package of variables. So let me try to quickly explain. The QA doc would be the text that takes into account both the question title and question body, and the answers, in case the answer bodies, because the answer doesn't have titles, for each question. So I just get everything, concatenate everything into a single thing for each row. So this is QAX doc. And then I have QX doc. QX doc would be only the content from the title plus the body. So it doesn't have the answer content.
Okay.
And then I have AX doc, which is just the content from the answers. And then and also, like, it's like a vector. Each row has one entry. And now I have AX caps doc, which is since I have 10 answers for each question. So here I have a 10 by number of rows matrix. That also, I mean, I don't use that a lot, but also depending on what I want to do, that might also be a more fitable format. So that just makes, I mean, it's the same thing, but represented in a different format. And then I have a Y doc, which is the score for each answer. And in this case, I have it separated by, like, I have for each single answer. I don't have a mean or something like that. So I have, again, 10 by number of rows, number of entries here. And also these first two here, going back, is the first one is QX tag. So this is a ordered dictionary, which is a kind of, it's like a regular dictionary, but it's ordered by something. So here I order by the popularity of the tag. So in a decreasing way. So I mean, the first one will be the most popular tag. The second one would be the second most popular tag, and then it goes. That's the reasoning, because that also is used by my models. So that's why I had to create something like that. And that's the tags for the questions. So also each question has tags. This is an information that is provided in the data dump. So I can just get these and mount this data structure that I need. And finally, I have QAX doc DL, which is it's similar to QAX doc, but here I have in a format of a dictionary, a list of dictionary. That's why I use DL to make it clear that there is a dictionary list. So I have a list. Each entry is a row in my data. So it's like the number of rows on the original file would be the number of rows in this list, and each list would have actually a dictionary. So I can consult the original fields by using the key, by using the column label as a key for this dictionary. So let's say I want to get the body of a specific row. I would just use the row index for the list, and then I'll use the column name as the key for the dictionary. It's a pretty easy way to, I mean, pretty much select the row and then select the column. That's a way to do that, but using two kind of different representations. But it's very efficient for Python, and it also makes very easy to get the row and the column that you want. This is very close to what Panda does on data frames. But since I'm not using Panda here, so this was actually I learned about Panda data frames a lot a lot after actually come up with this construct. So I would probably have used Panda instead of this one. But this, I mean, it works great for my case here. It's efficient, it's fast, it's easy to use, it's a good solution. So I believe it's clear right now what these are doing. So these two functions again is just to retrieve the data from actual files, text files. The first one being the knowledge base content, the second function being the question and answer content. And these two functions are on this library here. I'll also make it available, so you guys can try. Hi. All right, so let's proceed. Here I am in this block here. I'm using the count vectorizer function provided by scikit-learn. Also remember that I have imported numpy here, scipy, and two functions from scikit-learn, the count vectorizer and the tf-idf vectorizer. So this first block here is running the count vectorizer. The second block is running the tf-idf vectorizer. So before we proceed, let me just quickly try to explain what a vectorizer does. So we talked a little bit before about inverted index representation. So the inverted index is just a very common representation for text features. So for bag of word representations. So what it does is get a raw text as input, and then it will try to extract each feature as a word, as a term, and then that will be represented as columns in our inverted index, in our matrix. You can also call it just matrix because it's a two-dimensional matrix actually. So in this matrix, in this inverted index, each row, each document will be a row, and each feature would be a column. So it's the same as that design matrix on any machine learning kind of representation. So this is a really common way of representing the data. So, but if you have raw text, you don't have a direct way of actually having these features. So that's why you have to build it. You have to read the content for each row, and then you have to extract the terms. And then for each new term that you encounter, you will create a new column. And then in the end, after you process everything, you will have these matrix. And the number of columns will be the number of terms that you have on your original document that you used to build it. Right. Yeah. So this is very commonly also called bag of word representation because it just looks into individual words or individual terms present on the text. It doesn't take anything else into account. So that's why we call it bag of words. It's like taking the words and throwing into a bag and losing all further information that you could have. Then this is the basic concept. But after you do that, actually you have more than one way of calculating how important, how relevant that specific word would be, and also in which scope, because you can take a look at a word for a specific document or for a specific role, but you can also take into a look for this feature as a whole. I mean, for the whole set of documents or for the whole corpus that you have. So there's a lot of actually different ways of taking a look at it. And that's why we have more than one kind of vectorizer. A vectorizer is just actually counting let's talk about the first one to make it easier. The count vectorizer, which is this one, is just counting the number of occurrences for each term on that document, on that row. So it will process each row at a time. And let's say you have a, we will actually take into the examples in a moment. Let's say you have just 3 words, a simple, really simple document. So the first word would be the first term, and the number of occurrences would be 1 because you only have that word one time. Then the second one would be a different one. It also will have a count of 1 because it only happens one time. And the third one, let's say the third is a repetition of the first one. So in this case, I would not have like a third one. It will actually be an increase on the first term, and then my first term would turn into 2 for the count. So that's the idea. It's a pretty
Word frequency.
yeah, right. In other words, word or term frequency over the document. So it only looks the document at a time. In our second case here, what I'm doing is a little bit more complex. We'll take a look in a moment about how the TF-IDF is calculated. But for now, let's it's suffice to say that we will take into account that first information, which is the count for a specific document or for a specific role. And we will also take into account something called IDF, or inverted document frequency. A document frequency is a frequency of the term over the whole set of documents. So you're not here. You are no more looking into just one single row. You are looking into the whole set of documents, and you're gonna see how frequent that term is. That's the idea. I mean, that's not just 1 divided by the document frequency. So actually, the term IDF is a little bit misleading in that way, because it's actually a formula that you can use. And there's also actually different versions of this formula. That's not a unique, like accepted unique way of representing IDF. There's more than one way, but it's a formula. It's not just that. But the whole idea is that since it is an inverse document frequency, so it's like 1 divided by document frequency. So the more frequent the term is over the whole set of documents, the lower this score would be. So that's the idea. That's why we call it inverted or inverse. Okay, let's proceed. Now we can actually start running the code. And let me run this first portion here. So it will run, again, the knowledge base and the question loading. Actually, in our case, I don't even think we will use the knowledge base content. We will only use the content from the questions. And then it vectorizes using the count vectorizer, and then it vectorizes again using the TF-IDF vectorizer. So the output here is saying what has been done, and this is also a way that I started really liking to do stuff on Jupyter Notebook, which is trying to measure the time it takes for every single step. It can be maybe a little bit too verbose, but in my case, sometimes I have to wait a lot for a task, and I don't really have a precise idea of how much I'm gonna wait. Sometimes I wait like a couple of minutes. Sometimes I can let my computer run for hours. So this is an information that can be really useful for me, not for everybody, but for my case, it's really useful. So that's a way to quickly and easily know how much time it took for something to run. So in this case here, the thing that really took more time were the vectorizer itself. So it's pretty efficiently implemented in scikit-learn. It's very efficient because it uses functions from NumPy and SciPys. Mainly, it is efficient because of the sparse representation that it uses. So that's why it's so efficient. But still, it's not something so quick. Like this data set here, we have 5,000 rows, and it takes like a couple of seconds. So we are talking about, I mean, in megabytes, it's let's see. It's 20 megabytes. So, yeah, it's not bad, but it's also not, I mean, awesome. All right, so it's loaded. Next thing, let's say I want to know statistics about the size of each of these documents. So by size, I mean the number of characters for each of these. Let's run it, and then you can see that the average length would be around 1,000.
It is per row.
That is, yeah, by row, yeah, yeah. So when I say document, so it's by row, yeah. Each document is a row, right? So the minimum size would be 0. To be honest, I don't know which one is the 0 here. Probably a mistake that I left it empty. You should not I mean, I should actually have a zero-sized question in this data set. And the maximum one would be 28,000, almost 29,000. So it's pretty big, can be really, really big. Also, in this case, I'm looking into QX doc. So I'm looking to the content. All right, let's move. Let's say I want to actually take a look into the content. So here I can select the role, like I put row 3. So this is the 4th row that I have. Remember that it's an index, so it starts in 0. So 3 is actually the 4th. And then I'm printing the content, and you can see the content for the question. Now let's actually check the document frequencies. So here I'm defining 10 as the number of results that I want to check, but I can actually do whatever. Like, let's say you want top 5, top 100. I don't know. So just change it here. I'm getting the names of the features from the vectorizer. This is a simple way of doing it because it has this function that does it for us. This is a function to count the occurrence of a term in a document, but it only takes into account if it occurs or not. So if it occurs like 10 times, it doesn't matter. It's the same as occurring 1 time for this specific function, actually. And then I'm calculating the document frequencies. I'm getting the indices of these. I'm sorting these. I'm getting the indexes. I'm putting these into a list. This kind of list is actually, in this case, is actually returned by a n-dimensional array, not by ND array. But it's the same idea. Then I have the top features. Here I have a list comprehension to do that. Then I have the top DFs, and then I have the top indices. So now I can just print the indices, the features, the feature names, and the associated DFs. So let's see. So again, the first row is the index, the second is the term, and the third is the document frequency. So here I'm looking into the document frequency and not taking into account how many times a term appears in the same document. I'm only looking into actually the number of documents that has this term, just to make it clear, okay? And the difference from these to other cases, it will be more clear as we proceed. At least I hope. Okay, next thing, let's say I want to figure the position of a specific term. Let's say here I chose Python as a term, so I want to know where is it located into this sorted list. So it is sorted by the let's say frequency or popularity, right, of the term. And I can also actually sort depending on different metrics. So here I'm sorting on the document frequency, which is the one that we used on this previous block here. So if I run this, I will get the index, which is 131, and Python, and the number of occurrences on the document list. So if I had like for 5,000 documents, it will appear on 245. Next thing, I want to check for the same kind of ranked list, but in this case, I'm actually calculating the raw frequency. So what I call raw frequency, this raw frequency terminology is not so universally accepted. So be sure to understand what that actually is, because I mean, sometimes people call it TF, but it's not really TF. It's something else, because it's actually more like the DF, but not take into account just the occurrence, the binary occurrence. It will actually consider how many times each term occurs on every document. So take a look into the whole document set, document corpus, and then it will count the number of occurrences. And it does does it using this NumPy function called it sum. It's similar to the regular sum from Python, but in this case I can specify an axis. So I'm actually like in this. The idea is that I'm fixing the column and then I'm summing all the entries for this column. So since a column is a term, so I'm getting the whole number of occurrences over the whole set of corpus. So let's see here, the same procedure is done. So the code is pretty similar. And here I have the top 10 features using raw frequency. So again, I have the index, the term, and the raw frequency. Here you see already that the raw frequency is different from what you got before. Also, the terms are not the same. Like GT, he's the number one, while here's the third. So I don't have an exact correspondence because of the way it is calculated. It's not the same way. But if you take a look at the index, it should be the same one. Like here, the GT has an index of 2550, and here GT should have the same thing. If it doesn't, there's something wrong. We are doing something wrong. All right, next thing, check. Let's say I want to check the TF for a specific role. So for a specific document, let's say I want to actually look into the vectorized version of that document. So here I'm selecting a specific role, a specific document, like one. You can choose whatever, and then we can take a look at how it is represented. Like here, it is very common to have more than one as the frequency for the term, because we are using actually the title plus the body. So often people will actually use terms on the title and the body. So it's
so
right.
Is this like you're taking one row into consideration for this one document?
Yes.
And then you're like checking the TF for a given row. So that is like each term in the document, right?
I'm only looking into one single document.
Correct.
So I never look into something else in
Correct.
this case.
Case, format, string, title, all are in the same document.
Yes.
Correct.
Yeah.
Okay. And
like if I want to see the content of this document, I would use qxdoc, and then the same index, I'll be able to see the content of that. So like case should happen 2 times, like here and then here, and then format. And also because of the regular expression that I use, there are like small words or stop word that is not included. So that also is taken into consideration. Like I is not doesn't happen here because of the removal process. And then the next block, if you want to figure the position of a given term in the vocabulary ordered by the RF, it's similar to what we've done before, but we're just changing the metric. So instead of document frequency, I'm now considering the raw frequency. Yeah. So again, it will locate the term, the index, the term, and the raw frequency. Right. In the next one, we will want to check the top TF-IDF. So now I'm using the TF-IDF formula, and again, I will have different results as expected. Also, observe that the TF-IDF is not an integer; is a float. Actually, here I'm using the IDF because I could have calculated TF-IDF, but I just used the IDF. The IDF is actually the complex term, which it's more elaborate to calculate. The TF is just actually the term frequency. So we have calculated TF before. I could just get that information and multiply by the IDF. But here you see, like, by taking into account only the IDF, I'll actually change here to IDF to make it clear. Yeah. Then you see that the higher, the more rare that term is, right? Because if it is higher, that's because you have a low number on the denominator, So this actually is a less frequent term. So here probably we are looking to the less frequent terms of the.
You can keep it TF IDF and multiply it with the TF already calculated.
Yeah. If I multiply by TF, then I'll actually have the TF IDF.
It will not be like 7 point something. It will be something around a lesser value, right? It should be. Right?
Depends. It can be more than 7 because if I have a frequency of, I mean, if I have a frequency of 1, it'll be the same. It'll have a frequency of 2. The normalization process is done afterwards. So if I want to use the TF-IDF normalized version, so they have to calculate it and then apply the normalization. So after normalization, then the result will be between 0 and 1. But here I don't show the normalization step. Actually, yeah, right, yeah. In this case, it's not. Yeah.
It's not.
Yeah. I could get the actual TF-IDF also by just
modifying the TF value and giving a long for this value.
No, I mean, because I ran the vectorize already. So the result for the vectorized, the end result is actually the matrix with the TF-IDF. So I could just consult that. That's also like a way I could do that. Like here, yeah. Here's the matrix that would have this information. We got it?
So this matrix has the TF-IDF values, or it just has the IDF values?
Yeah. There's also something that I failed to mention. When you are using the vectorizer, there's actually 2 steps to be done. The first one is the fitting. The second one is the transformation. So the fitting is for the TF-IDF, it will calculate the IDFs, because the IDFs has to be calculated over the whole set of documents, right? You cannot just look into one single row and calculate it. You have to look into the whole thing. So this is the fitting process. So the IDF is calculated. The first step, sorry. The second step would be the transformation step. So the transformation is when you get these IDF, and then you multiply by the TF, and then you have the final TF-IDF for each term and each row of your inverted index matrix. Okay. You can also you can do that 2 ways actually in scikit-learn. You can call the fit and then call the transform, or you can use the fit transform in a single step if you are using if the corpus that you want to use, the vocabulary, let's say, you want to use, is the same as the document that you want to use.
Okay.
Because not always that will be the case. Like you can have a vocabulary that doesn't match 100% your document. Like here, I'm using the transform 2 times. So in the first step, I'm using the QA, which is a more broad kind of corpus because it includes both the Q and the A, both the questions and the answers. And in the second step, I'm only taking into consideration the Q. So the vocabulary would be the broad one, but the result would be only for the Q in this case. Okay, so the last thing that we can do is actually do what we have done before, specify a term, and then just taking a look into where that term would be located into our sorted IDF list. So here that would be the 5962 index with for the term Python, and the IDF would be 3.59. Before we wrap up, let me just show the scikit-learn's source code for the TF-IDF for the vectorizer. I'm just going into the documentation of scikit-learn's website and selecting source. That's how I get here. And then I end up in a GitHub project. All right, so I just want to show you guys the calculation for the IDF. I'm not gonna explain detail. I mean, by detail. If you are curious, you can take a look at it. It's also a good exercise because they use a lot of different features. Like they use a lot of NumPy functions, a lot of SciPy functions. They use object orientation on Python. They use pretty much everything that Python offers. So that's a good exercise to learn Python. If you take a look at the code. Yeah, here's the part of the code that calculates the TF-IDF. So they have actually two versions of TF-IDF, the smoothed version and the non-smoothed version. The only difference is that the smoothed versions avoids zeros. So it just sums 1 to the document frequency and to the sample size, the number of actually not the sample size. This formula here, the final IDF is summed by 1, and the smoothed DF is also summed by 1. The number of samples is also summed by 1. Yeah, this is these two steps here is the smoothing steps. So here these are Boolean parameters that you can pass to the function, and it just convert into an int. So if it is true, it will become 1, and then 1 is summed over the whole DF. In this case, DF is not a scalar; it is a vector. So it will just sum 1 to every single element of this vector. And that's because of NumPys. That's the behavior that NumPys provides for ND arrays. So that's how the summing, the plus overloading occurs. So after you do the smoothing, it's calculating the document frequency. So here there's a this is just actually the frequency. I mean, it goes over. That's how exactly the same thing that I did for calculating the DF, not the IDF, the DF part. So it will look over the whole set of documents. Count how many documents has that term, and then it will return the DF for that term. In this case, it's done in a single step, so it's done for the whole set of terms. Here we talked about this one. That's the smoothing. The number of samples is the number of rows that you have on your data. So it's just the number of documents that you have. And the number of features would be the number of unique terms that you have. So this is actually the resulting shape of your inverted index representation. And that will be used. The number of samples actually is used in the formula of the TF-IDF, so that's why we need that. And then we calculate the IDF. Here's the more important part. Let's say we calculate by the log of the number of samples divided by the document frequency, and then we sum to 1. So it's a log of a division, and the DF is calculated as we told before, and the number of samples is just the number of documents in your collection. So then you have the IDF calculated. So you just in a further process, in a last step, you just multiply the term frequency by the IDF, which is this thing that you had calculated. That's it. All right. The things that I like to have shown you guys, I showed everything. If you guys have any questions, I hope it was interesting and clarifying somehow.
Are you using this for your thesis?
Yes, I'm using it a lot. Yeah.
What are you doing for your thesis?
What am I doing? My thesis is about trying to predict answers for questions on Stack Overflow. So like proposing answers to questions on Stack Overflow, but I don't use the like other questions or answers from Stack Overflow itself to try to answer it. I use what I call knowledge bases. So these are data from external sources. So I collect those from online references like language APIs, language references for different libraries and programming languages. So in my case now I have 6 different knowledge bases. So I have a knowledge base for Java. I have a knowledge base for Python, a knowledge base for JavaScript, one for Android. What else? One for PHP. Yeah, that is a 6th one that I'm not. I can check. Django. Yeah, I have Android, Django, Java, JavaScript, PHP, and Python. These are the knowledge base that I have now. So
how are you like predicting what are you taking into consideration to predict the answer?
I try to use similarity measures. So my main representation is a vector space representation. So it's a TF-IDF representation, and I calculate the cosine similarity of the entries. So I take, it's a pair. So I compare. I mean, I get a question from Stack Overflow, and I get a knowledge base entry from the set of my knowledge bases. So I compare this pair, and I come up with the similarity. So I have to do that actually for every single combination. So the similarity matrix happens to be a 2-dimensional matrix with the 1 dimension for questions and 1 dimension for knowledge base entries. So I just look. So after I do that, I can just search for the most similar like knowledge base for a given question, because the kind of problem is an information retrieval problem or a search problem. So I have to use a query to consult like an input, and then I will receive as a response the most similar document to that query. So my query would be the question, and the answer would be the knowledge base entry. That's how the similarity is calculated. So in my case, I like for a given question, I just fix that question, that role, and then I look for all possible similarities, and I can rank these. So I get, like, in my case, I get the top 10, and then I use a metric to. I have a semi-automatic way of generating the ground truth to evaluate my system. So it's a formula that I came up with that it tries to identify these similarities when you have a really high similarity compared to the others. So it's like detecting an outlier in a set. So when I have this case, I can provide. I usually provide between 1 and 3 good matches from the ground truth. I can also create the ground truth manually. That's something that I actually am planning to do in the next days. I mean, in a small set to compare. What?
We can't do that for everything. It is going to take.
Yeah. I have to do that. I mean, a small set, because I don't have infinite time to do that. And then, but in this way, I can evaluate my system. So my system, the baseline system, works like that. So I use the tag information to leverage to increase the performance of this retrieval. So I can use the tag information 2 ways. Like, if I have the tag for a question, which is not always the case, I can just get that tag, and by using the tag, I can filter the right knowledge base for the answer.
Don't you have filters for everything?
What?
Don't you have filters for all the things? the filter? Don't you have
Filter.
it for all the?
I mean, it only makes sense to use filters for the knowledge base that I have. So
Exactly. So
yeah, so I get like I define the tags for my knowledge base, and then I search for the same tag into the question. That's what I do. There's an idea that I'm working with Wei Chi. It's a student from IST also. He was here the other day. I'm not sure you guys met him. Yeah, so he's trying to develop a clustering mechanism. So this each of his cluster is based on a tag cloud.
okay.
So we'll try to use that information also as a way to relate these two things and see how it goes. That's also a different approach to that. And I also have a classification, like a classifier that I use to predict the tag.
Yeah.
No, just to predict the tag. So
Just the tag. Okay. Okay.
Yeah, so it gives me like good results between 65 and 85% accuracy. So it works, I mean, okay, and it also is able to increase the performance of the retrieval process. So if I use the exact, like the right tag, sometimes I have an increase of even 70% in the scores. But sometimes can be as low as like 20%, but it's still an increase, a significant increase. Even, I mean, it's not bad. Yeah, it can be not awesome, but it's not bad, right?
Not bad.
Yeah. And the metrics that we use in this case is, I mean, it's not like classification metrics. So it's like the most significant metric that I use is called NDCG. I'm not sure if you have heard before, normalized cumulative gain, discounted cumulative gain. Sorry. Yeah, this is like is a metric that
it's like a part of the whole matrix.
No, the normalization part is what makes it go from 0 to 1. But because there's also DCG. So DCG is a weird metric that gives you like a not very clear result. I mean, result to compare to other systems. The normalized DCG is a more trustworthy kind of measurement because you can use to compare even two systems or two situations in the same system. It's a good metric. So the idea that is the first results are a lot more important than the following ones. So it's a logarithmic scale. So the first one is really like there's a really high relevance, and then you can also associate not ranks, like relevance scores to each of the results. In my case, I'm not doing that. So in my case, I have like a binary relevance, which is just a document, a response is either relevant or not. But for normalized discounted cumulative gain, you can even have more than 2 possible relevance scores. But I'm not really using that now. I mean, you don't have to use. The most important thing is this behavior that it just, I mean, the first result is amazingly more important than the second, and then the second is amazingly more important than the third, and then they go the same thing it goes and goes. So that's pretty much the idea, and it just does that by doing a simple count in the numerator of the ranking, the ranked result, and the denominator would be a logarithm, a log of something. So that's just that. That's it. The system is working already. I've done everything, but I didn't write anything yet. I have to start writing. And also, we are trying to organize my system with the other system from Wei Chi to make the two of them work together and see how it goes. I mean, if we got good results, we are thinking about writing a paper, submitting a paper. That's what we are doing right now. I'm also, I mean, a lot of time I spend, I mean, reading papers. So like in the last week, I didn't actually code a lot. was more like reading, a lot of reading. And sometimes you have to like fix small things, and then you come up with an idea. And since my code is already kind of too big, and now to manage it, sometimes it takes like more than 1 day to do a simple thing. Yeah, but it's an interesting. It was really interesting to me to actually be able to learn the tools. Like I use a lot of scikit-learn. The most used library is by far scikit-learn. And like NumPy, you have to learn a lot of NumPy also to optimize the calculations. There are some steps that sometimes I think I can still further optimize, because right now I don't, on my notebook there's a certain limit of the data of my sample size that I can still run on my notebook, but after that I can't. Like if I use LDA and some metrics to change the scores, or to do a metric calculation called KL divergence. It's like cosine similarity, but it's a different formulation. So if I do that, it's very, very, very CPU intensive. Actually, both CPU and memory intensive. So if I go up to 20,000 rows, I can still run on my notebook on these more complex codes. You know, for the simplest codes, I can even run the whole set. It runs, but more complex codes is really complicated to run on my machine. So I don't know. I mean, I was thinking maybe, I don't know, some kind of optimization that I could do to make it.
So you can always do that later.
Yeah, right. Yeah, it's not like the most important thing, but that's something that since you are always coding. Yeah. Sometimes you just spend time with something that you shouldn't really. Yeah. Nobody's perfect. Yeah, that's it. In the beginning, I spent a lot of time in the pre-processing. In the pre-processing, I mean generating these files and filtering, and like I in the beginning I tried to use the original format that they provided the data, which is a set of XML files. So I spent a lot of time trying to do that. So I just, at a certain point, I just gave up and decided to convert everything to CSV. So that was something that really paid the effort, because it's a lot easier to process, a lot faster than XML to process.
But if you like say try passing,
it is still recording. I'll just stop here. See you guys.